Wait. Hi everyone. Today at the seminar we are hosting Karol Węgrzycki. Karol, please start.
Hi, nice to give a talk at the Algorithm Seminar at University of Warsaw. This is a joint work with Karl Bringmann and Marvin Künnemann. And most of this work I've done when I was at University of Warsaw, but now I have moved to Saarland University. So this talk is about all-pair shortest path problem. And in this problem, you are given a directed graph G with some positive edge weights. And the pretty important thing in this talk is the upper bound on the weights, and the upper bound is W. And the task is to compute the shortest path distance between all pairs of vertices. So, for example, you need to output n square numbers, and for example, the distance between blue and red vertex is 5 on this graph. And I don't know if you have seen the OLED STOC from last week, but the best algorithm basically runs in n squared time and cubic time, and then there's an ongoing hypothesis that you cannot get a strongly subcubic running time, even when the weights are polynomially bounded. So that being said, what we have to do is we have to somehow manage this. And usually we manage this by settling for approximation. So the central problem in this talk is the approximate all-pair shortest path problem. And in this problem, you need to compute the 1 plus epsilon multiplicative approximation of all pairwise distances of all vertices. And the best algorithm runs in n omega divided by epsilon times log W. And it's due to Ulrich's fig from 2002. So omega is a time of the fast matrix multiplication, and it's n to the 2.373. And this is quite important problem, and because it gives us the similar bound for approximate graph characteristics such as diameter, radius, and so on. And this is the best algorithm that we know for directed graphs when we have the n epsilon, and for undirected graphs when epsilon is bounded by 1, and do something clever when epsilon is large in undirected case. So before I proceed to our result, let me talk about SFIX algorithm. So recall that it runs in this time. And to do that, I will need some subroutine, and the subroutine is min plus product. So in this problem, you are given two matrices of real numbers, and their min plus product is basically the product in the min plus semi-ring. So you need to output the matrix C with entries ij, such that when you have a matrix A and matrix B, you need to do this matrix multiplication, but instead of multiplication here you take plus, and instead of plus here you take minimum. So it's pretty convoluted definition, and the best algorithm is naive. Actually, due to Williams, it's slightly subcubic, but yeah, you can do the cubic algorithm by just naively computing, taking every entry and then going through every k here. And other algorithm runs in W times n omega. And W is, recall that W is the maximum weight in this matrix. So when we have this algorithm in hand, then what SFIX proved is that if you can approximate min plus product in say this running time, then you can approximate all shortest paths also in this time. And basically the reduction is, in the reduction you are given this adjacent matrix, and you add the self loops, and you put these self loops as 0 loops, and then you just perform log and approximate min plus product subroutine with this squaring procedure, and then at the end you output this distance to be the distance between these vertices. So that's what STOC proved. And to arrive with this,
is it the same epsilon there?
No, not
Okay,
really.
yeah, I think.
But it's up to some constant.
Yeah. Okay.
So you have to adjust this up to logarithm, I think. Yeah, we don't really care about logarithms with this O tilde notation. Okay. So then what happens is, okay, now we are ready to compute this 1 plus epsilon approximate min plus product. So when we do this in this time, then we compute all per shortest paths, approximate all per shortest paths in this running time, okay? And basically it's the scaling algorithm. So you are having this scales 1, 2, 4 up to W. Let's assume that W is some power of 2. And when you arrived at some scale, first thing what you do is you remove the entries in this table A and B that are greater than 2 times Q. And then you round the entries of A and B to be multiples of epsilon Q. You lose some epsilon factors then, and you scale all the entries by 1 over epsilon Q, and then you run the exact pseudo-polynomial algorithm from min plus product. So you have this property that W is now order of 1 over epsilon, and the running time is n omega divided by epsilon from this, and also you have log W scales here. And this is basically STOC algorithm, STOC scaling algorithm. Okay, so this is the definition again. This is the algorithm, and you can ask several questions. So, for example, can you improve the dependence on n? And it turns out that probably not, because it would give us automatically the fast algorithm for Boolean matrix multiplication. And also, if you would improve this dependence on epsilon to be some little of, to be 1 over epsilon to the little of 1, then it would violate the APSP hypothesis. You can try to get the square root of epsilon here, but getting something like logarithm of 1 over epsilon here is probably a dead end. So the question that we state in this paper is, okay, what about log W factors? Can you actually improve this algorithm and get rid of this log W factor? So this kind of algorithm that doesn't have this log W factors are called strongly polynomial time algorithms. And basically the reason that we care is that usually the input to such problems is represented as a floating point numbers. And this log W can be arbitrarily fast. But I'm not saying that it's really practical algorithm. Still, we have this n omega here, and yeah, it's not really practical. So the interest of this talk is basically a theoretical one. So before we proceed, can we actually get a log W? Can we actually get rid of this log W factor here? Like the input already consists of n squared times log W bits. So does this question even make sense? And so I will consider the following model of the numbers in this talk. So basically the running time is the number of arithmetic operations on RAM model. So if you analyze this Xfix algorithm again, then it uses exactly this number of arithmetic operations. So in principle, n omega divided by epsilon arithmetic operations will be possible. So in the paper, we also consider more involved or restrictive models such as bit complexity with floating point, but getting rid of the slot W factors in all of them is plausible. Okay. So in this talk, I will consider the following input format to the APSP problem. Okay, so the numbers are given as floating points. So the floating point is just two numbers. It's the number x and number y. We call x to be a mantissa and y to be exponent. And now when we have this pair in hand, then they will both represent the number that is 1 plus x times 2 to the y. So now note that we can basically approximate these numbers at the beginning, and we will have lot 1 over epsilon bits of mantissa and lot w bits to represent the numbers up to w. Okay, that's pretty hard to grasp at the beginning. Okay, can I proceed? Okay. So now let me go through the main algorithmic results. So this was our question. And it turns out that actually for graph characteristics, you can do this. You can approximate diameter, radius, and all of this characteristic in n omega divided by epsilon time. And this is pretty easy. I will talk about this at the very end when everyone will fall asleep. Moreover, you can approximate all per shortest path on undirected graphs in n omega divided by epsilon time. This is what we wanted. But the most intriguing part is that you can approximate all per shortest paths on directed graphs in this n to the 2.69 divided by epsilon time. And what is pretty much surprising is that this is equivalent to the min-max product. So this is this factor is the min-max product factor, the running time of the exact algorithm to compute min-max product. And the main theorem is basically this last one. And I just want to briefly mention the motivation of this result. And this is basically the first strongly polynomial and subcubic in n approximation to all per shortest paths. And this is also important because this is an equivalence between approximate and exact problem in this fine grained complexity field, which is pretty unusual. And this also, if you think about this as an algorithmic result, then this also gives us some conditional lower bound on this approximate APSP algorithm in directed graphs. So this is basically the motivation part, and now I will proceed to the part when I actually show how to prove this theorem. So basically, the ingredients, the first ingredient is the mean plus product, which you have already seen. And this first ingredient is the equivalence between mean plus product and APSP, which you have also already seen. And the other ingredient is the min-max product. So I haven't defined it yet, but it's basically the same as mean plus product, but replace plus with max. And the thing you need to know about min-max product for this STOC is that it can be computed in this n to the 2.69 time. Also, it's known that this min-max product is equivalent to all pairs bottleneck paths. So what we need to prove is the equivalence between min plus product and exact min-max product, between approximate min plus product and exact min-max product. So this we already have by Zwick. This we have by Wasilewska-Williams. And this is what we are going to prove. So yeah, this is what I mean by the equivalence. Okay. Okay, let me proceed. So since we are proving equivalence, it means that there is a reduction from approximate min plus product to min-max product, and from min-max product to approximate min plus product. So first, let me show to you how to get approximate min plus product by using exact min-max. Okay. So the observation is that, first observation is that you can actually compute the two approximation by just running min-max product once. Okay. And it's basically because, this is equal to the sum of the elements up to factor 2. So if you multiply it by 2, and this by 2, then you will have upper bounded and or lower bounded this by factor 2. So the goal now is to reduce factor 2 to 1 plus epsilon, and this is our main combinatorial theorem. So it's pretty hard to grasp. So you are given two matrices, A and B. And what I'm claiming now is that there are S matrices, A1 up to AS and B1 up to BS, where S is some 1 over epsilon times log n, such that this sum of these elements for every I and j is approximated by the is equal to the maximum of these elements for some layer, and for this minimum layer, it's equal to the sum up to a factor 1 plus epsilon. So that's basically what sum to max covering theorem states. Okay. So if we would have this sum to max covering in hand, then it is pretty straightforward how to approximate this min plus product. You basically compute a min-max product for every layer, and you choose the minimum for every entry. And this is an approximation up to 1 plus epsilon. So the running time would be the time to compute the min-max product times the number of layers. And there is 1 over epsilon of these layers, so the running time is n to the 2.69 divided by epsilon. Okay. Okay. So if we would assume the sum to max covering, we have proven this reduction. Okay, and the other direction is not that straightforward. Yeah, in this other reduction, we are basically using this assumption about the input to the problem. So first, note that if we exponentiate the numbers, then sum basically becomes maximum. So if you exponentiate the number a by some 20 to the power a plus 20 to the power b is basically equal to the 20 to the maximum of them, up to a factor 2. And the idea is, and then if you would take the logarithm of that, you would have the maximum. So basically the reduction would be, okay, so you take every entry in A and you compute 20 to the A, okay? And then you execute this approximate mean plus product routine for some constant epsilon. And then you just take the logarithm and round to the closest integer. Okay. However, the numbers got exponentially large. So normally you would you would have the linear time. This exponentiation would take the linear time. But let me present to you the input format to this problem. So in this exact min-max product, the integers you are basically given the integers, and to represent one integer you need log w bits. However, in this approximate min plus product, your input is a floating point numbers, and they are upper bounded by w. And to represent integer up to a w, you need only log w bits. So basically, to exponentiate the number, you just copy the integer just copy the input integer from this exact min-max product, and you copy it to the exponent of this floating point number, and you put that constant as a mantissa. So if we assume that the oracle to this approximate min plus product is given floating points, then we can do this.
But I don't understand one aspect here, if I might interrupt. You are assuming that the oracle is able to perform computation using this specific representation.
Yes, that's exactly what I'm assuming.
But it has to be able to do it, right? It has to be an oracle that is able to operate on large numbers.
Yes.
And this is like this is not a restrictive assumption, like the existing algorithms for approximating APSP are doing.
They are doing this.
Okay, thanks.
So it's not really a problem. Yeah. So basically, to prove this equivalence, we do the reduction from approximate min plus product to min-max product by exponentiation, and to get the fast algorithm for approximate min plus product, we use this sum to max covering. So what is left is for me to prove the sum to max covering to prove this equivalence, basically. Okay, so this is what we are going to do now. Okay, so let me recall the sum to max covering. Yeah, this is going to be a little technical. And to prove this, we split the proof into two cases. So in the first case, we call a pair of numbers distant if A divided by B is at least 1 over epsilon or smaller than epsilon. Okay, and when on the opposite case, the numbers are called close. Okay.
So here we are talking about vectors, and previously it was about matrices. So it was not important that those were matrices. It actually applies to vectors.
Yes.
Okay.
You can think about this as a n-square long vector. It will apply to this. I'm talking about vectors to not keep this ik, bjk, bkj numbers all around this theorem, but you can apply it to vectors, to matrices. And it's also useful for min-max convolution. If someone is interested.
I was going to ask this, whether it's important that the coordinates mix or do not mix. So the coordinates, because when you are just doing a matrix product or a vector product, then I coordinate only ever interacts with I coordinate. And there is no mixing between different coordinates. But when you are doing convolution, every coordinate interacts with every other coordinate.
No, it's not really important here. We're just proving this theorem, and we're using this as a black box. Okay, let me go to the pretty cool combinatorial stuff now. Okay, so now we are in this case when we are in a distance covering. So these two numbers are distant from each other. Then basically you need to compute their sum, and you will have the 1 plus epsilon approximation with maximum, right? So what we must do in this case, we must avoid close pairs and put plus infinity when we have a pair that is close. So that's basically the idea here. Okay. So first, what we do is we will split this. Z is the sum of the A and B. Okay, and we have sorted this Z, and we will split this this Z, which is the set of all the numbers in here, into chunks. So into locant chunks, and we will split it into 2, into 4, and when the distance between these pairs, between the endpoints of this chunk is smaller than 1 over epsilon, we stop splitting. So by distance I mean you take the rightmost number here and you divide it by the leftmost number here, and when it's smaller than 1 over epsilon, then you stop splitting. Okay, so we have locant levels of a lot of chunks. So let's look at the
one. So that is sorted.
That is sorted, yeah. So here you have the largest number, here you have the smallest number, and here you have a median. Okay. And what we will do now is we will have 2 cases for each level. And note now that if you have a red chunk here, and all the numbers A in here, and all the numbers B in this red chunk, then they have to be distant by 1 over epsilon. Then they have to be with distance greater than 1 over epsilon. Right, because of the way that we have defined this splitting, that we stop splitting when the distance is smaller than 1 over epsilon. Okay, so we take all the numbers A in here and all the numbers B in here as a one single level, and the same for this blue blue chunks. And for technical reason, we have to do this twice. To have this guarantee that this distance is at most 1 over epsilon. However, there is still a slight problem. What would happen if you have a number A in here and a number B in here? And then they would never, and they are of distance greater than 1 over epsilon. Then they would never be considered in this covering. Okay. So we fix that pretty easily with straightforward method. So if you have a number A in here and number B in here, we just consider log 1 over epsilon shifts. And the property is that, okay, so you take the number here and you divide it by 1 over epsilon, and you keep only the numbers that are of greater distance than 1 over epsilon here. And then what you do is you multiply by 2, which is what this next figure presents. and you consider this as a consecutive layers of this covering. And then the property is that the first property is that only 1/epsilon far elements are selected. And then if you have any A and any B that are of distance greater than epsilon/2, then they will be in some cover. And then you will have this nice property that when A plus B are distant from each other, then they are approximated by max. Yeah, I was pretty fast here, but I hope you get the ideas without the details. And now let me tell you what will happen when we are in this close setting. So when this A divided by B is, for example, 1, then the sum of these elements and the maximum may differ. It can be like 2. Then we have to somehow modify this A and B's to get this. So what would we like to do ideally is to take B and make it to A plus B. If you would do that, then maximum of A and this B prime would be A plus B. Okay, that's pretty crazy what I'm saying, but because we don't really know what A is beforehand, so how can we do this? But luckily we can approximate, and this is what we will exploit. So fix some integer D, okay? And then what you do is you remove all entries of A that are outside of this 1 plus epsilon to the D minus 1 and 1 plus epsilon to the D. So only the numbers in this red region will be non-infinity. Okay, that's the second step. Then you remove all the entries of B that are outside this epsilon, outside of this region. So only the B's inside this blue region will be non-infinity. Okay, and you add value 1 plus epsilon to the D to every element of B. Okay, and then you have this magical property that maximum of A prime plus B prime, maximum of A prime B prime is equal to B prime, which is approximately A plus B. Yeah, but the problem is that there is an infinite number of integers D here. But we can do this for 1/epsilon integers D on the same level at once. So this is what we are exploiting here. That let's say that B was here. And then when we would add this A here, then it will be here outside of this blue region, and even adding it to this A it will not matter. So there is no interaction between this.
Why are the interactions between them not an issue?
So if you have a B here, and you will add this A here, you will add this. If you add this here to this B, then it will be much smaller than this A here, than this here. And when you will take the maximum, you will still approximate it up to epsilon.
It's because the gap between them is so huge that it doesn't matter.
The gap is 1/epsilon. Okay, and this basically concludes that.
But how does it help us?
What? This thing.
I probably didn't get it. How come we don't have an infinite number of possible Ds now?
So we are basically considering only 1/epsilon Ds.
You are looking at the abstraction classes.
Okay.
Modulo S or something.
Okay. Okay.
Okay. So this basically concludes the proof of this combinatorial theorem that we have proven. And so now let me tell you something super simple and nice that usually works when you want to get rid of this log W factor. So the first thing is that we can actually approximate diameter in this strongly polynomial time, and we can approximate all per shortest paths in undirected graphs in this strongly polynomial time. Okay. So let me start with approximate APSP in undirected graphs. Okay, so here is an algorithm. So first thing what we do is we iterate over every scale, and it already gives us log W thing here, but it's only for the analysis. Okay, we will get rid of this soon. And consider what will happen if we will add only the edges in this scale to this. Yeah, we initialize this graph H as an empty graph on this and vertices, and we will add the edge of weight in this scale to H. Okay. Then we round down all the edge weights to be the multiple of epsilon Q divided by N. This is because now, when we are in this scale, we know that the what's the distance between these pairs, and then and we scale in such a way that this W is basically N divided by epsilon, because here, and then we execute this algorithm of Zwick, and then what we do is we contract all edges that are of weight 0 in this H. So the weights, the edges that were of that was that small that didn't really matter for us. Okay. Now, so the algorithm is so for the correctness, the algorithm is correct. We round we round all the values to be these multiples of epsilon Q divided by N, so we lose only epsilon divided by N factor. And since all the paths are of length N at most, since all the shortest paths are of the length N, then we don't lose much, and we can contract. So this is the only difference we have with the directed case. So this only works because we can contract all the edges here. Now for the analysis, then note that any pair of vertices will be considered in this for loop only for this polylogarithmic in N many rounds. Because when it's smaller, then we will just contract it. So it means that let NQ be the number of vertices in this graph H in this particular scale Q. So the total number of vertices in all the scales is N squared, and hence the total running time is, and the running time then is this NQ divided by omega, NQ to the power omega divided by epsilon, and in total we arrive at N omega divided by epsilon. Okay, so this was pretty unexpected for us, but it only works because of the fact that we can contract edges in undirected graphs. Yeah, usually people ask questions here, but I guess.
What is the reason why? What is the reason why we can contract the edges in the directed case?
we cannot contract, or
Yeah. Are we?
In the directed or undirected?
Directed, right? Because
No.
here we contract in the undirected case. Why don't we use this in the directed case?
So you cannot contract edges in the directed graphs, and if you contract edges in the directed graphs, you will change the answer to the upper shortest paths.
I'm still processing what just happened. So.
Yeah. I was pretty amazed too.
But each edge is rounded multiple times, right?
Yeah.
In many phases.
No, this is just so.
Oh, that's interesting because that's how I understood it. So,
no, sorry. You add edges of this weight to this edge, and you keep the previous best edge weight in there, and then you round down all the edge weights that are present in this edge to be this epsilon q divided by n. So
you round down the new edges?
Yeah, I round down all the edges in H. I don't change H here, okay?
Okay.
And then I execute, I have some H prime here, and I execute this subroutine on this H prime here. Yeah, sorry for not being that precise here. So the point is that when I have only edges of this, I know that approximately what is the answer between, what should be the answer between what's the worst answer that is that is reachable in this practices, in this scale. Yeah, this is not really that easy to grasp. Okay, let me go to the approximate diameter. It's a little simpler, okay? So in this approximate diameter, you are given a directed graph, and you want to find two edges, two vertices that are basically of the, you want to find the approximate diameter, approximate maximum distance. So before we proceed, let GW be the copy of G. When we remove all the edges of weight greater than W, and we just change all the weights to be exactly W. So the graph is basically unweighted, but basically weighted but all the weights in GW have the same weight. Okay, so this is what GW is. So first observation is that if you are given W, then you can compute two approximation of a diameter in GW in n omega time, because the graph is basically unweighted. It has some, Okay. So now note that if the two approximation of GW is infinity, then diameter has to be greater than W. Yeah, because it means that basically graph is, there are two vertices that are not reachable. And when it's finite, then the diameter is at most W times n square, because yeah, there are n square edges. Yeah, that's some
Makes sense, yeah.
So our algorithm is basically you first find the smallest W such that the diameter of G is finite, and you can do this by binary search. You don't really need any log W here. You can just sort the edges and yeah, look at the median vertex and do the binary search. So now assume that we have found such W. It means that we have n square approximation to our diameter by the previous assumption. So now what we do is we round all the weights to be multiples of W divided by epsilon, W times epsilon divided by n square. And we run this approximate n omega divided by epsilon W algorithm. Okay. And this is good enough because we allow 1 plus epsilon approximation, and rounding this weights here, that doesn't matter for approximation. Like we will lose some constant in epsilon factors. So that's the strongly polynomial algorithm for diameter. Log W here will be bounded by the ratio between largest W is n square n to the power 4 divided by epsilon, because because we have rounded up the weights to be multiples of this W epsilon divided by n square. Okay.
Very nice.
And maybe I should tell this algorithm first before paying first, but it's basically the same idea here. Have this approximation in hand, and we are rounding up adaptively. Yeah, and this is pretty general reduction. I thought I will find some nicer application of it, but this reduction works. This reduction to approximate diameter works when you return only one number, or when you are having this minimization or maximization algorithm, and when you are given this weakly polynomial algorithm in hands. And it means that it works basically for radius, minimum weight cycle, graph median.
How do you define approximation on the median?
Median.
You are looking for a vertex that has the sum to all vertices in the graph approximated that approximates multiplicatively the sum of distances.
Let me check it. I don't remember.
Because graph median is minimizer on the sum of distances.
Let me check. I don't really remember how we define this median. Sorry for that.
I mean, if you have all pair distances, then I think it's pretty much straightforward.
Yeah, I don't remember. Sorry for that.
Yeah, but most probably it's what Przemek said. The natural definition.
Yeah, I don't remember. Okay, and there are some nice open problems. So can we get a faster min-max product? So see Oleg's talk on this amazing breakthrough in all pairs LCAs in DAX. So can we get n to the 2.499 algorithm for min-max product assuming omega is equal to 2? Another intriguing question is, can we get a faster algorithm for min-max convolution, or rule out that you cannot get any better with current techniques? Yeah. Another questions are, I guess no one really looked, or I don't know that many papers on strongly polynomial dynamic or distributed graph algorithms. So can you reduce this number of rounds of polylog n log w to polylog n log w somehow? Yeah, another question is about more application of sum to max covering. I don't know more application outside of this approximate or per shortest path and approximate min plus convolution. Yeah, and I thought that the last question would be the easiest, but I don't really know the answer after a year. So can you get a strongly polynomial approximation for minimum cycle mean? So this previous reduction doesn't work because it's not a minimization or maximization problem. And currently it is an omega divided by epsilon log to the power of third w. And that's it. We also have some results for min plus convolution and tree sparsity problem. Yeah. So thank you.
So I have one question, because you said that a much stronger dependency on epsilon would violate APSP, but there is no obvious reason against like I don't know, square root of epsilon.
No, it can really happen. It happens for min plus convolution.
Oh.
Yeah, you can strongly approximate min plus convolution in n to the 3/2 divided by square root of epsilon. And you can weakly approximate min plus convolution in n divided by epsilon time. In strongly polynomial regime, it happens for min plus convolution. Yeah,
this weakly approximation is your result, right? This is your
not
your
really.
result.
It was done by Indic in Soda 7.
Okay.
I think.
Okay, sorry. Confusing papers.
Yeah, we only improved some log factors there. Yeah, but intriguing question is, can you get square root epsilon here, for example, or square root epsilon here? I guess you need something different than sum to max covering. I think at some point we had some lower bound on sum to max covering.
So this is probably a stupid question, but I lost it somewhere. What was the relation of these two min-max product? Specifically, because there was some, right? I remember.
Relation.
On the very first slides, you said that the.
Tell me when.
You mentioned the Duan and Petty algorithm and the equivalence with all pairs bottleneck paths, right? Yeah. So what is the relation of the min plus and min max?
You mean?
Specifically, I would like to know what happens and if anything happens if we improve min max product.
So if you improve min-max product, then you will improve your paper, for example. You would improve bottleneck paths. You would improve also our result.
Okay.
So all of these results would be improved. Which means that improving min-max product is pretty important problem.
Yeah, but your result does not say that, like, doesn't give some evidence that this is very hard, undoable, or
No.
okay. That was my impression, but I
It
would.
depends how do you define hardness. It means that there are two problems that people were thinking about, and they share the hardness. One is equivalent to another.
Okay, yeah. In that sense, min-max product is pretty hard to improve on, probably. Yeah. Okay. Makes sense. And you also mentioned this strongly polynomial, like the open problem, that maybe we can get strongly polynomial time algorithms for like dynamic version or in distributed settings. So
yeah, I'm not really sure what I mean here.
Okay.
I've tried fully dynamic APSP, but I don't have anything there.
I see.
Okay, I will stop the recording.